Hello and welcome to another Calc 3 video. In this video, we're going to talk about equations of lines and planes. So we're going to start out with writing the different forms of the equation of a line, and that's going to lead us to the equation of planes, and then we will end the video discussing distance. So starting at the top, to write the equation of a line, we're going to need two things in 3 space or even in 2 space. We're going to need a point and we're going to need the position of the line. So if we look at the figure, we're looking to write the equation of this line L. So first thing that we know is we have this point x naught y naught that's on the line. And then we need to know the position of the line. In this case, we're going to take a look at this vector v, which is parallel to our line. Okay, so the idea with writing an equation of a line is that we have this vector that goes to a point, and then we have another vector to just some point P. Point P being any point on the line. So then, this vector right here that goes between P and P naught, we call vector A. And we can see that that vector A on the line is parallel to this vector V. So A goes from the initial point, or the point on the line, to any other point. And if A is parallel to V, then it's a scalar multiple of V. Right? Parallel vectors are scalar multiples of each other. So what that gives us then is the vector equation of a line. Vector equation of a line. So R naught denotes a point that's on the line, the vector that's to that point, and then this TV is the direction of the line, or the position. So every value of t is going to give us a different point on the line. For positive values of t, wherever our point is, we're going to be getting points on the right of it. For values of t that are negative, wherever our point is, we're going to get points to the left of it. So that's the vector equation, or the vector expression. Another expression is to write that together. So R, we're going to write as x, y, z. R is just a point on the line. Now remember, it's a vector, but we're looking at the vector that gets us to that point. This R naught is some point that's on the line, and our vector v is a vector that is parallel to the line. So far we have this vector equation, which we often write in component form. And that's going to lead us to parametric equation of a line. Parametric equation of a line, we're just going to write 3 parametric equations. So that would be parametric equation of a line, which is the line that goes through some point and is parallel to the direction vector. Okay, so that's the start of writing the equation of a line in 2 space or 3 space. We need a point that's on the line, and we need a vector that's parallel to the line, or what we call a direction vector. So let's take a look at example number 1. We're going to find vector and parametric equations for the line that passes through 4, 2 and is parallel to -1, 5. Okay, so if we start with our vector equation, R then is going to be our initial point, 4, 2, written as a vector, remember, so this is just the vector starting at the origin that goes to 4, 2, plus t times our direction vector. Okay, that is the vector equation. If you want to leave your answer like that, that's great. Or sometimes what people will do is they'll write it in I and J notation. So that is also acceptable. Or lastly, they'll choose to put the I components and the J components together. So this is 4 subtract t times I plus 2 add 5t times j. So any of those are acceptable for the vector equation. Parametric equations then, we're going to have x equals and y equals. X is just going to be the first components. So that's going to give us 4 subtract t. Y is going to be the second components, so that's going to be 2 add 5t. So those are the vector or the parametric equations for that same line. So a quick note for us is that these equations are not unique. Not unique. That's really important. We could choose a different point or a different parallel vector. Now, we were also asked to find two other points on the line. You would just plug in a value of t. So let's say that we want to plug in t equals 1 to the parametric equation. We would get x is equal to 4 subtract 1, or 3. Y is equal to 2, add 5 times 1, which is 7. So another point on the line would be 3, 7. And again, you could do that for a second point, just plugging in a different value of t. Okay, so moving on to another example, if you think all the way back to geometry, a common question you were asked is, given 2 points, find the equation of a line. So we're going to do that in this example. Find parametric equations of the line that passes through P1 and P2. Where does the line intersect the xy plane? So in order to write the equation of a line, we need a point, and then we need a parallel vector. Well, if we find the vector P1, P2, that, of course, is going to be on the line, which means it's also parallel to the line. So 5 subtract 2 gives me 3, 0 subtract 4 gives me -4, and then I get 8. So that is our parallel vector. And then I'm going to use this point P1. So my x is going to be 2, add 3t. My y is going to be 4, subtract 4t. And my z will be -1, add 8t. So those are the parametric representations of the line. Now, keep in mind, any vector that is parallel to this initial vector will work, which means that any scalar multiple will work. So any scalar multiple of that vector will also be parallel to our line. And then the second question is, where does this line intersect the xy plane? Well, remember with the xy plane, our z value is 0. So if we take this parametric equation for z and set it equal to 0, we know that we're going to intersect the xy plane when t is 1/8. So then if we plug 1/8 into our representations for x and y, we can say that the line intersects at the point 19/8, 7/2, 0. Okay, so if 2 forms of a line was not enough, you're going to be happy because we're going to look at a third representation right now, which is called the symmetric equation. So if we take our parametric equations, we notice in each of them we have a t. So we can solve for t then. When we solve for t, these are the equations that we get. So what our symmetric equation is going to look like then is when we set all of those t values equal. So we get x subtract x naught over a is equal to y subtract y naught over b is equal to z subtract z naught over c. So that is called the symmetric representation of a line. So if we want to write the symmetric equations for the example that we did above, we would get x subtract 2 over 3 is equal to y subtract 4 over -4, which is equal to z plus 1 over 8. And I didn't mention this earlier, but in order to write these equations of the line, we could have chosen either point. I just chose the point that I wanted to, but we could have used that second point as well. Okay, so then normally t can be any real number, -0, positive. So the question is, what happens if we limit the value of t? Like we say t is from -1 to 1 only, or 0 to 5 only. Well, hopefully this makes sense. If we limit t, we are going to get a line segment. So we won't get the whole line, we're going to get a portion of it with a starting and an ending point. So let's take a look at an example of what that would look like. Example number 4, find parametric equations. So first thing, have to be parametric, for the segment joining P and Q. Okay, so again, we're going to need a point, which we have. we're also going to need the vector joining those points, or a vector parallel to that line. So if I look for that vector, I'm going to get 3, -4, 8. So then I'm going to start with this starting point. So I'm going to get x equals 2, add 3t, y is equal to -4, add 4t, and z is equal to -1, add 8t. Now that's the whole line. That's the whole line. We need to limit t though. If we plug in t equals 0, we're going to get that first point P. And then if we substitute in t equals 1, we're going to get that point Q. So this right here in black would be the parametric representation for the segment that starts at P and ends at Q. Now, written differently, you're going to see this formula to the right. It's the same idea as what we just did. So if we wanted to follow that representation instead, we could do 1 subtract t. I'm definitely not going to have enough room. Sorry, I'm going to start again. We would do 1 subtract t times our starting point, which is 2, 4, -1. Add t multiplied by our second, which is 5, 0, 7. And that would end up giving us the same representation that we came up with. Again, though, t has to be between 0 and 1. Okay, we have a few more questions, really one more question that has to do with lines, and then we're going to build on that and take a look at planes. Okay, so consider the two lines that we're given. I want to know, are the lines parallel? Do they intersect? So the first thing that I'm going to do is I'm going to write these vectors in, or write these lines in a vector equation. So for the first line, x, y, and z is given by the point 1, 5, -1, add t times 4, -4, 5. Second line is given by x, y, z is equal to the point 2, 4, 5 plus t multiplied by 8, -3, 1. Okay, so if we look at our two position or our two direction vectors, it's these two vectors right here, and the first thing that I can tell is that these are not scalar multiples of each other. What that means then is that these vectors are not parallel. So these vectors are not parallel, hence our lines are not parallel. Okay, so then the next thing that we need to know, we know these lines are not parallel. Do they intersect? Okay, so here's where we're going to need to be a little careful with our notation. That first line, any value of t, I'm going to let that be t1, is going to give us a point on that first line. A separate value of t will give us points on that second line. So if I plug one value in of t, that'll give me a point on line 1. If I plug in a separate independent value of t in the second line, it will give me another point. So what I want to know is, do those points ever exist at the same time? So I want to know, is there a time when x on the first line is equal to x on the second line, and y on the first line is equal to y on the second line, and z on the first line is equal to z on the second line? Well, for our x's, we're going to get 1 plus 4t1 is equal to 2 plus 8t2. For our y's, we get 5 minus 4t1 is equal to 4 subtract 3t2. And then for our z's, we get -1 plus 5t1 is equal to 5 plus t2. Okay, so we have a system. We have a system of two unknowns. So let's see what we can figure out from here. From this first equation with x, I'm going to get 4t1 is equal to 1 plus 8t2. So t1 then is 1/4 plus 2t2. And I'm going to substitute that into my equation for y. So I get 5 subtract 4 times 1/4 plus 2t2 is equal to 4 subtract 3t2. So this gives me 5 subtract 1 subtract 8 t2 is equal to 4 subtract 3 t2. So t2 then is 0. t1 then is 1/4. Okay, so then we have to ask ourselves, what does this information mean? What does this information mean? This means that when t1 is 1/4 and t2 is 0, L1 and L2 have the same x and y. So when t1 is 1/4 on the first line and t2 is 0 on the second line, our lines have the same x and y. So the question then is, what about z? Well, if we plug those values in, -1 plus 5 times 1/4 is equal to 5 plus 0, we can see that those are not the same, which tells us that L1 and L2 have different z values at these two values of t. Hence, there is never a point or a value for t1 and t2 where these two lines have the same exact point. So these lines do not intersect. So this is a little bit of a throwback to geometry. How is it possible that we have two lines in 3 space that are not parallel and they don't intersect? What does that mean? Well, hopefully you remember this piece of vocabulary. This means that the lines are skew. Skew lines are lines that are not parallel and do not intersect. We only have skew lines in 3 space. Okay, so that was lines. We're now going to build on that and talk about planes. So as you can see, there's 4 objectives at the top, so there's a whole lot that we need to talk about. First thing to know about writing the equation of a plane is that a vector parallel to the plane is not enough information to determine the equation of the plane. And that should make sense. If you picture right now a plane that has a point and a line on it, there are infinitely many planes that go through that same line and point. Okay, so instead then of having a vector that is parallel to the plane, instead we need a vector that is perpendicular to the plane. So that leads us to this first equation of a plane. We have a vector perpendicular, and then this here, r0, is going to represent the vector for a point that is on the plane, and then r is just going to represent the vector for any point that is on the plane. When my notation covered it up, when we dot these two, we should get 0. And that should make sense. Remember that the dot product of two vectors that are perpendicular is going to give you 0. Well, in this case, we have two vectors that's perpendicular. Another way to write this is this alternate form. Here's our normal vector. And then here is the difference between any point x0, y, x, y, and z, and then a point that's on the plane, x0, y0, z0, and we should get 0. When you multiply that out, you get what's called the scalar equation of a plane. So one thing to know is that these equations are not going to be unique. Again, like the equations of the line we found before. There are many points that you can pick on the plane. There are many normal vectors you can pick. So there's not just one equation, one possible equation. Okay, so let's take a look at an example. Find an equation of the plane passing through that point and perpendicular to that vector. Again, an equation means that the equation we come up with is not going to be unique. So what we're going to need to do is take our normal vector, 4, 2, -5, and we are going to dot it with x subtract 3, y plus 1, z subtract 7, and because they're perpendicular, that dot product is going to be 0. So this is our vector equation. If you want to leave it like that, that's great. Sometimes people will multiply it out. That's also great. You can leave the equation like that. Or lastly, sometimes people will combine all the like terms and get that last form, which is called the linear equation of the plane. Okay, so one thing you also have to be able to do is you have to be able to graph a plane. Graph a plane. Okay, so it's not going to be helpful to graph a plane in terms of a point and a perpendicular vector. That's just a little much to wrap our brains around. So instead, let's think about how do we determine a plane? So back in geometry, how did we determine a unique plane? And we said we can define a unique plane with 3 points that are on that plane. Okay, and they cannot be collinear. So we can't choose 3 points on the same line. So the question is, how do we easily come up with 3 points that are on this plane? Well, come up with the intercepts. So you use the equation of the plane, find the x, y, z intercepts. You can graph those, and that will be a quick sketch of the plane. Okay, if we want to get into something a little bit tougher, like example 7, we're going to find an equation of the plane that passes through 3 points. Okay, so to write the equation of a plane, of course, we need a point, and we have 3 of them, and we need a vector that is perpendicular to the plane. So that's the question, is how do we come up with a vector that is perpendicular to this plane? Well, if I find vector PQ and I find vector PR, the cross product of those 2 vectors will be perpendicular to the plane. So let's start by finding vector PQ. And that's going to be 2, -4, 4. PR is 4, -1, -2. And then again, if I choose my normal vector to be the cross product of these 2 vectors, I'm going to have a vector that's parallel to the plane, or perpendicular to the plane, rather. So that's my next step, is to find the cross product. If you trust me, I'm not going to show the work. I'm just going to tell you this ends up being 12, 20, 14. So if we want to use that vector, we certainly can. But remember, any scalar multiple of this vector is also going to be perpendicular to the plane. So if I decide to divide this by 2 maybe to get myself some smaller numbers, I can do that. So that's the vector that I'm going to use. And I'm going to use this point 1, 3, 2. So the one equation of the plane is 6 times x minus 1 plus 10 times y minus 3 plus 7 times z subtract 2 equals 0. And again, you can leave your plane in that form. Or if we multiply everything out, we get 6x plus 10y, add 7z is equal to 50. Or subtract 50 is equal to 0. So there's a whole bunch of different formats you can leave your answer in. Okay, so let's keep going now and get into a little bit of some tougher questions with these planes. In example 8, it says, consider those 2 planes. Part A, find the equation, find the angle between the 2 planes. Okay, so our first plane has a normal vector of 1, 1, 1. Our second plane has a normal vector of 1, -2, 3. Okay, so then we know that cosine of theta is 1 vector dotted with the second vector over the norm of each vector. So if I do that, dot product will give me 1, subtract 2, add 3. The norm of one vector is root 3. The norm of the other vector is root 14. So I get cosine of theta is 2 over root 42, which tells me that theta is about 72 degrees. Okay, so then the question is this what we're looking for? Is this the actual angle between the 2 planes? And the answer is yes. You're going to have to do a little bit of picturing here with me. But picture that you have 2 planes, and you have these normal vectors. The angle that we just found between the normal vectors is opposite of the angle that we're actually looking for. So the 2 planes and these 2 normal vectors are going to form a parallelogram. So again, sorry, this is a little hard to picture, but you have your two planes and you have your normal vectors from those planes. And when you draw all of that, you get a parallelogram. So the angle that we found between N1 and N2 is across the parallelogram from the angle we're looking for. And because they're parallelograms, they're going to be congruent. If that's confusing, please ask me in class and we can certainly talk about it some more. Okay, so then, part B, we need to find symmetric equations for the line of intersection of the two planes. So what we're going to need for the equation of a line is we're going to need a point on that line and a parallel vector. So first thing that we can do is we are just going to find some point that's on this line. And we are going to choose the point where the line intersects the xy plane, which means that z is 0. So if I use my first plane, that is going to intersect the xy plane at x plus y is equal to 1. And then if I use my second equation, that plane is going to intersect the xy plane at x subtract 2y equals 1. So now I've guaranteed that both of these planes, we're looking for a point where the z is 0. If I solve this system, what we can see is we're going to get 3y equals 0, so y is equal to 0, and x is equal to 1. So both planes have this point 1, 0, 0. And to verify, you can go back and plug into those two equations that we have. And we see that 1, 0, 0 is in fact on both of those planes, which means it's on their line of intersection. So we have our point. We still need a vector that is parallel to the line. Well, if the line is on both of these planes, so if, I'm going to call this line L, so if line L lies on both planes, then it must be perpendicular to both normal vectors, which I called n1 and n2. Okay, so what we need to do then is find that vector, which we're going to do, of course, by the cross product. So I'm crossing the first vector, which is 1, 1, 1, with 1, negative 2, 3. And again, I'm not going to show the work, but it ends up being 5, negative 2, negative 3. If you trust me. So lastly, what we're doing is we're writing symmetric equations for the line that has this parallel vector and goes through this point. So we're going to get x subtract 1 over 5 is equal to y over negative 2 is equal to z over negative 3. And as I've said multiple times, these are not unique. This is not a unique representation, so there are a few other representations as well. Okay, last thing for us to talk about with these equations of lines and equations with planes is distance. So let's move on to our last set of objectives. Last thing that we're going to talk about, it's 4 objectives, but they all relate to the same equation, and the same idea is finding distance. Finding the distance between a point and a plane, between a point and a line, so on and so forth. 2 parallel planes, 2 skew lines. So here's the theorem that we have up above. The distance between a point and a plane is given by this equation. Okay, so some things to point out to make sure that we are careful of. With the plane, our plane needs to equal 0. So if it's not equal to 0, we need to make sure that we get it equal to 0. And then secondly, in this numerator, we have some absolute value bars. Okay, so there's a few different ways that you're going to see this. So let's take a look at this first example. Find the distance between parallel planes. parallel planes. So the first thing I want to talk about is what that box at the side says. How do we know that these planes are parallel? We have our first normal vector on the first plane is 1, 2, -2. Second normal vector is 2, 4, -4. These are scalar multiples of each other, which tells us that our lines are parallel. Okay, so for this distance formula that we have above, we need a point and we need a plane. Well, we already have two planes, so let's just pick one of them. So let's say that this is going to be the plane that I use. So then all I need is a point on this first plane. On that first plane, if I make y and z 0, x then is going to be 3. So we should see that the point 3, 0, 0 is on that first plane. And then our second plane is 2x plus 4y, subtract 4z is equal to 7. Now, as I noted above, though, we're not ready to use the formula yet because our plane is not set equal to 0. So the first thing that we're going to do, or the next thing really, is to take that plane and subtract 7 so that we are now set equal to 0. So using our equation, our point gives us x1, y1, and z1, and then we have a, b, c, and d. Jumping into our distance formula then. In the numerator, we have absolute value of a times x1, so 2 times 3, plus b times y1, plus c times z1, plus d, all over the square root of a squared plus b squared plus c squared. And if you simplify all of that, I'm not going to show you the work, but you end up with a distance of 1/6. So that is the distance between our two planes. Okay, and then last example, finally, is example 10. Example 10 is going to go back to the lines from example 5. In example 5, we showed that these lines were skew. So we now need to find the distance between them. In order to use that distance formula, we need a point and we need a plane. So let's just start by choosing a point on L1. And it might be easy to choose t equals 0. So if we plug in t equals 0 to that first line, we're going to get the point 1, 5, -1. Okay, so then from here, we need to figure out what plane are we actually looking for. So what plane are we actually looking for? Well, if we have skew lines and we have a point on one line, we need a plane that goes through that line 2, or that line 2 is on. Okay, well, in order for us to get a plane, we're going to need a point, and we need a perpendicular vector. Well, the point on L2 should be easy. Choose again t is 0, so that corresponding point on that second line is 2, 4, 5. The question is, how do we get this perpendicular vector? So that is a vector that is perpendicular to line 2. Well, if we take line 1, the vector on line 1, and cross it with the vector on line 2, we're going to get a vector that is perpendicular to both. Now, do we care that it's perpendicular to line 1? No. Just happens to be the case. Okay, so if I take my two vectors here, so my 4, -4, 5, and then 8, -3, 1, and cross them. So I'm taking the normal vector, or the parallel vector rather, from the first line and crossing it with the second line. The symbol you use doesn't matter. So the first line is 4, -4, 5, and the second one is 8, -3, 1. Okay, ignoring the row and column that I comes in, we're going to get -4 subtract -15. For j, we switch the sign, and we get 4 subtract 40. And then for k, we get -12 subtract -32. So that gives us 11, negative 36, and 20. So again, that is a vector that is perpendicular to both lines. It's perpendicular to both lines. If we remember, what we're trying to do is write the equation of a plane that goes through L2. So we now have a point that is on that plane, and we have a vector perpendicular to that plane. So writing the equation of the plane, we're going to get 11 times x subtract 2, subtract 36 times y minus 4, add 20 times z subtract 5 is equal to 0, which gives us 11x, add 36y, add 20z, add 22 is equal to 0. So finally, we're ready to find the distance. We have our plane, and then we have our point from the very beginning, which is on the other line, which is 1, 5, negative 1. So just taking a second to review, we have a point that's on line 1, and we have a plane that goes through line 2. So our distance then, using that formula, in the numerator, I have a times x1 plus b times y1 plus c times z plus d. And then in the denominator, I have the square root of a squared plus b squared plus c squared. And this does not end up looking real nice. It's 167 over the square root of 1,817, which means the distance between these skew lines is about 3.918 units. And that's it. We finally made it. We talked about lines, we talked about planes, we did some distance. I know this was a long video, but I sincerely appreciate the time you spent with me to go through it. If you have any questions, please make sure you ask in class.